All right, so today we're going to wrap up the calculation that we were doing at the end of the last lecture about concerning entanglement growth in this brickwork circuit, and then we'll sort of move on to kind of see how the structure that we observe in this calculation, which is this essentially what we've boiled the calculation of the purity down to in the brickwork circuit is the calculation of the free energy of an Ising domain wall in the ordered phase of an Ising ferromagnet. And that kind of universal structure will appear all over the place in not just completely random unitary circuits, but also in circuits that have additional conserved quantities. And we'll try to at least give some big picture of how this might emerge, but focusing on the case where there's really minimal structure. Okay, so to recap from last time, what we showed by the end of last lecture where we were at was to show that if I take this brickwork, and also please let me know if my handwriting is too small. If I take this brickwork circuit and I calculate the purity, that this is equal to this partition function for an Ising magnet. So I'm going to draw space and time in the quantum circuit still, right? And so this is a two-dimensional classical statistical mechanics of an Ising magnet. There's an Ising symmetry in the bulk, and the boundary conditions in this magnet are fixed by the choice of initial state in the dynamics and the observable that I'm calculating, right? So the initial state shows up here. Let me just write it as, the product state that we chose was this zero state everywhere here, right? Really, I have something like 4 copies of it appearing at every site because I'm calculating the purity. And then up here, I have this contraction that I'm doing that if I define this region to the left of this point as the A bar subsystem and this region to the right as the A subsystem, then I have this contraction where I have the upspin states over here, and then the downspin states that are being contracted to the right, right? So in the sort of StatMech problem, so this is maybe if I viewed this as a tensor network, this is the contraction that I'm doing with an appropriate initial state and a final state. And these boundary conditions I refer to as domain wall boundary conditions. And I'm taking A to be semi-infinite, so the system size is infinite. I'm not going to discuss saturation of the entanglement at long times, et cetera, yet. And so these are domain wall boundary conditions in the StatMech problem, and these are free boundary conditions, right? So what the domain wall will do generally is it'll take some sort of directed path, and because the system is infinite in the spatial directions, it'll end on the sort of temporal boundary, which is the initial time. You can think of it as the initial time of the circuit, right? Dynamics. Okay, and we argued that this quantity should decay exponentially in time, basically because with some constant that we'll show right now, basically because the Ising magnet is ordered, and you can actually just rewrite this as the cost in free energy to add a domain wall into this ordered phase. Right? So this quantity is like the ratio of 2 partition sums and is therefore exponentially small in the free energy costs that you incur to do this, right? So, okay. So a technical point that we ended on last time, which I'll repeat just because it was a little bit, maybe a little bit fast, but is basically left to you as an exercise, is that so microscopically, if I look at this Ising magnet, I have a situation like this. I have a honeycomb lattice. And the reason is that I have this brickwork circuit with 2 Ising spins per unitary in this brickwork architecture. And that gives me a honeycomb lattice. So there's an A and a B sublattice. And I referred to one of the spins on one of the sublattices, say, is the sigma spin. So this is maybe a microscopic view of some part of the honeycomb lattice. This is one unit cell, and these are some adjacent sites. So if I refer to these spins as tau 1, tau 2, and tau 3, right? So there's some weight here associated when I do this partition sum. There's a weight that's calculated, and the weight here is given by this Weingarten function, right? Which showed up in this expression for P2, which I wrote down a while ago. And the weight here is just given by the overlap of this state, right? And a more convenient representation is to actually just integrate out, is obtained by integrating out the sigma spins everywhere. And this is on, say, the A sublattice of the honeycomb lattice everywhere. And since prior to this, we only had interactions on bonds, this gives rise to these 3-spin weights. These 3-spin weights are invariant under the Ising symmetry transformation applied to all of the tau spins, just inherited from the original Ising symmetry. So this Weingarten function is only a function of the product of sigma and tau. So it's invariant under flipping both of them. And these overlaps are trivially so as well, right? Okay, so then after doing this, we obtain the following weights. So on every downward facing triangle, now in terms of the domain walls, so I have these spins, say tau 1, tau 2, tau 3, but instead of denoting the state of the spin, I'm just going to draw on a dual lattice whether there's a domain wall that's passing through the bonds of the lattice. So there's weight 1 if there's no domain wall. There's weight 0. This is what we discussed last time. If there's a domain wall that passes through like this, and these are both consequences of unitarity of the circuit, you'll see actually in the, maybe Roman will discuss this, but in dynamics with measurements, these rules don't actually hold anymore when we broken unitarity. And then the final weight, right, since there are only 4, is given by a domain wall that's kind of passing downwards through the circuit, like this. And this is given by Q over Q squared plus 1, where Q is the Hilbert space dimension of the qubits, okay? So this is where we left off last time. And let me just pause here to ask if there are any questions about this before moving on. Yeah. What is the lattice that I'm drawing the domain walls on? Yeah, so after integrating out the sigmas, what I'm drawing here, so the lattice sites are just where the tau spins reside, and the bonds are just going to connect the tau spins together. So it's a downward facing triangles essentially are where the weights reside. Okay, I'll draw that again in a moment. So it's a triangular lattice. Are there any other questions? Yeah. Say again, and when you integrate out. Oh, that this is 0. Is that what you're asking? Oh, because I've well, it does because I've done the summation over the Weingarten function in order to derive these weights, right? So maybe I can maybe discuss this sort of offline, but well, I guess I left it as an exercise, but maybe I can just, so this is, what is this weight? This is, you can write it like, so you have the Weingarten function for some configuration involving sigma, but I want to sum over sigma to derive some 3-spin weight. And the way I would do that is, so this sigma doesn't actually exist anymore. I'm summing over it. Sigma is plot up or down. So this is given by sigma tau 3, and then I have this overlap sigma tau 1, sigma tau 2. So this is what I'm evaluating. This is the expression for the 3-spin weight. Yeah.
There's like a prior reason that when we integrate out sigma, we get like positive weights. Like, could it be the case that even after you integrate out sigma, you have negative weights and you can interpret that as a static one?
Yeah. That's a good question. So the question was whether, what the intuition is for getting positive weights after integrating out of sigma. Maybe I can discuss that offline. It's true that for higher moments, like trace of rho to the n, we don't really have a general way for arbitrary local Hilbert space dimension to do this kind of transformation. When the Hilbert space dimension is large, though, we're able to do this. But the intuition for the existence of these weights comes from thinking about unitarity and what happens in the limit of large local Hilbert space dimension. But we can chat about that offline since those are sort of technical points. Yes. No, so there are no weights anymore on the upward facing triangles. They're only on the downward facing triangles. I'll draw that in just a moment. And so you can ask me that question again if that doesn't. The weight's 1, like any configuration on the upward facing triangles is permitted. Yeah. I'll draw it. And if it's confusing, ask me again, or I'll call on you again. Okay. Yeah, it's basically because of the choice of spin that I'm integrating out, right? Yeah. If I integrated out tau, I would get, weights on other, triangles pointed the other way. Okay, so great. So now we're kind of, we're in business. This calculation is actually pretty straightforward. We can't create domain walls in the bulk of the system. They can only be created at the boundaries. We have a domain wall boundary condition, and we know exactly what the weights are for the domain wall to propagate through these downward facing triangles. So all we have to do is to calculate this weight and sum over the different independent trajectories of the domain wall. And that's very straightforward to do. Let me continue that here. So the lattice that I have looks something like this. It's a triangular lattice. Let me just draw it for one time step of the brickwork circuit. So remember that each time step of the brickwork circuit involves a unitary on even and odd bonds, and then odd, or even and odd sites, and then odd and even sites, right? So you can imagine that every unitary in the circuit kind of used to live on the center of every downward facing triangle. So this is like one time step in the brickwork circuit. This is some delta t, right? Okay, so what have we said? We've basically just said that so this is my A bar subsystem, say, is referring to the Hilbert space to the left of this point, and the A Hilbert space lives to the right over here. So what we're saying is that the spins are locked in this up state here, and they're in the down state over here. So I have an Ising domain wall in this triangle that's been nucleated, okay? And it can do something like this. It can enter this triangle, it can move over here, it can do anything at an upward facing triangle. But because of the boundary conditions, it can't go back and end at this interface, right? It has to propagate downwards, so it goes down and maybe does something like this, et cetera. And so it continues in the temporal direction, right? Or reverse time in the quantum circuit, okay? So this is the top boundary of that, the top boundary that I'm drawing, right? So we know what these weights are. So we see that there's basically 2 downward facing triangles the domain wall encounters per time step of the unitary circuit, right? And there's 4 paths that it could have taken here, right? For every downward facing triangle it encounters, it could turn left or right, right? Okay, so then what's the answer for the purity? Well, putting this together, so the domain wall ends at this sort of ends at the spatial boundary that lives, the temporal boundary at the initial time of the circuit. So putting this together, what we would conclude is that the Haar averaged purity is just given, so it's given by a weight Q over Q squared plus 1. And this weight is raised to the 2t, right? So there's 2 downward facing triangles per time step and t time steps in the circuit, right? Okay, so that's the weight, but then we have to multiply by the entropy. And what is the entropy? It's, 2 to the 2t, right? Every triangle that's encountered, the domain wall can go left or right. So this is the answer, and this is exact. Okay, are there questions about this? Great. So this calculation was fairly straightforward. This is the entropy. And this you can think of as the energy of the domain wall. Right. So we've done this, and as expected, this decays exponentially in time, right, with some rate that depends on the size of the local Hilbert space dimension Q. And now we should ask, well, okay, if we we've calculated the purity. We've seen some interesting behavior. What we really want to calculate is something like the entanglement entropy, right? Which is, the purity of a very large subsystem is going to be exponentially small in time. It's not something we can easily measure. And also, it's not obvious how it's related to, say, our ability to, classically represent one of these one-dimensional states by an MPS, et cetera. So we might want to be interested in, so we should ask, basically, what about the, say, expectation value? And I'll worry about the expectation value first before discussing a typical Haar random circuit. What about this? Where this is my shorthand for the von Neumann entropy. For the Renyi entropies, I'll keep the superscript, but for the von Neumann entropy, which is the n going to 1 limit, I'll drop the superscript generally. So this is the von Neumann entropy. So what is this quantity? This is what I really want to know, right? And okay, so to make progress, let's first ask what the second Renyi entropy is doing, which is so what I could ask about is the expectation value of minus log of trace row squared, right? So that would be the Haar average of the second Renyi entropy instead of the Haar average of the purity. And well, something very simple we can say. Something very simple we can say is that, yes, there's a question. Oh yeah, the entropy comes from summing over all the different paths the domain wall could take, right? So the
Q is the weight of a path.
that Q over Q squared plus 1 just comes from that lowest line over there. Yeah.
Thank you.
Okay. Yeah. Yes, you can, but the problem is that this weight prevents you from coming back down. You can't, because you have to, so maybe I was quick about this, but so let's say I let me choose a new color. Let's say I did that. So you're saying that I do something like this. Let me go down further. So I go to this triangle and then I go back up, right? But if I go back up, I either have to go up this way and try to end at this interface, which I can't do. The system is semi-infinite, so there's no spatial boundary here where I can end, or I have to do something like this, and the weight for that is 0. Yes. Yeah, so eventually you can convince yourself that you have to either end on this boundary or incur one of those 0 weights. And perhaps that isn't obvious, but so let's say I go back up. So, and then I can go here. I can try to end here, but I can't do that, right? Or I go down like this and I incur 0 weight. So that's the problem. Yeah. Yes, I'd encourage you to go through this yourself if that's confusing, because it's a detail, but it's an important detail. Yeah. Yeah, Leo.
The spins are just dummy variables of summation of projection.
Yeah, that's right. Yeah. Yeah, exactly. So I'm using after doing the Haar average, I have just this tensor network I'm contracting, and the spins are a way to organize that summation that happens when I contract the tensor network, right? Yeah, so the projector projects onto the subspace spanned by 2 states, which we labeled up and down, right? There's a question, yeah, so that's where this labeling comes from. Yeah, I wouldn't call it the 2 components of the projector. I want to emphasize that they're not orthonormal states. So, but yeah, but there are states that span that Hilbert space. So we can label all of our configurations by those 2 states. Any other questions? Yeah.
Can you translate this to a finite
Yeah, that's right. So I'm not discussing what happens with the finite system size, but when you have a finite system, the domain wall can also end on the left end of the system or the right end of the system. And yes, so that's how the entanglement entropy will eventually saturate, right? Because that's energetically favored, right? But I actually won't spend that much time discussing saturation of the entanglement in this lecture, just because I have to go through. There are other things I want to cover, but I'm happy to discuss that offline. Yeah. Yes. Oh, because every downward facing triangle, at every downward facing triangle, of which there are 2 per time step, the domain wall can take a left turn or a right turn. Right? So there's 2 options here and 2 options here. So there's 4 options per time step. Right. Right. Yes, exactly. This is, as I wrote down earlier, maybe I erased it. This is, this is 1 time step, what I'm calling 1 time step of the circuit. You have the odd, yes. So it's, it looks kind of statistically time translation variant. Yeah. 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 No, it's similar. You'd get the same answer. No, you get upward facing triangles now. So the geometry is different, but the calculation is, yeah. That's a technical point, but you should get the same answer. Yeah. Leo. Yeah. So log of this expression is not the minus log of that is not the Haar average second Renyi entropy, right? I have to average the logarithm of this quantity. I don't want to take the log of the average. So I'm going to discuss that right now. Yeah. I think in random matrix theory, this function appears all the time. It's I mean, people talk about Weingarten functions for a specific group over which you've defined the Haar measure. So yeah, right. It connects to, I think, the representation theory of the symmetric group. There's a neat expression for the Weingarten function in terms of cycles of permutations of sigma and tau. So I don't know if it was studied in that context outside of random matrix theory, but. Okay, so now what I'm going to do is to argue that the von Neumann entropy actually has a very similar behavior to what you would get if you just naively took minus log of this expression, right, of the expression that we've derived. And the point is just the following. So recall or note that that this, if I take a function f of x, which is minus log of x, this is convex, right? Okay, and what that means is just geometrically, it's easy to draw. If I, this is minus log x, x. So if I take any 2 points, right, and I draw a chord connecting those 2 points, then the function always lies below that chord, right? That's the geometrical meaning of convexity, right? And mathematically, all that means is that f of t. So let me call this point, this is x1, and this is x2. So mathematically, all that means is let me write it and then explain. Okay, so all this means is that if I evaluate the function at some point that sits between x1 and x2, right, I'm going to sit below the chord, and that's just expressed here, right? This is the function evaluated at that point, and this is, some weighted average of the function between those points that sits on the orange line, right? So that's convexity, but that means something very nice for us, which is basically that basically the log of minus log of what we've calculated provides a lower bound on what we want to calculate if we were to Haar average the second Renyi entropy. Okay, so this means actually let me continue this on the other board so that since I want to continue writing more inequalities. So this means that minus log, I'm just going to write expectation value R trace rho A squared. This is less than or equal to the expectation value over the R measure of minus log trace rho A squared of T. Okay. This is true. And this itself is upper bounded, right, by the expectation value of the R measure over the R measure of the von Neumann entanglement entropy, right? So this has to do with convexity of the log. And this just has to do with what we discussed last time, which is that the Renyi entropies for larger Renyi index M are non-increasing, right? And this is true, this inequality is true for every realization of the Hart circuit and is obviously therefore true when you do the average. So we found a lower bound on how the entanglement entropy actually grows in the circuit when you do the Hart average, right? And now we can compute a nice, upper bound also. So an upper bound, this is a bit of an aside. It might be familiar to some of you. So an upper bound on any Renyi entropy in any quantum circuit, so unitary quantum circuit, is given by the following minimum cut prescription. This might be familiar to some of you. Okay, and the prescription I'll state without proof, and the proof is like 2 lines into the notes, or I can discuss it offline for those of you who have questions about it or aren't so familiar with it. So given a state psi, which is generated by a quantum circuit. So I have in mind something like this. It's funny, whenever I want to draw a circuit that isn't brickwork, I find it very hard. Okay, so this is nearly brickwork. Okay, but it doesn't really matter for purposes. Okay, etc. So this is the time direction. Okay, it's almost, it's really almost brickwork, so forgive me. But so given a state psi generated by a quantum circuit, so I run the dynamics starting from, say, some initial product state, and then this is my time t, and I have my state psi, right? We draw a cut, which I'll call gamma. And let's say I'm interested in, again, calculating the entanglement So let's say I want to calculate this is my subsystem A bar, and this is my subsystem A, right, to the right of that cut. And let's say I want to calculate the von Neumann entropy or some entanglement entropy of A. So what I do is I draw a cut gamma, which does the following things. It starts at the ends of A at the final time of the circuit. So this is where my state lives. And it passes through bonds. of the circuit. And it ends at a spatiotemporal boundary. I guess I'll say at a space-time boundary. Okay, so in this case, what would I do? I can start, I have to start my cut at the boundary of A. There's only one boundary. The system I'm taking is semi-infinite. So A is a semi-infinite system. I'm only interested in its growth, the growth of entanglement, say, starting from some product state. So I start my curve gamma here, and I can't pass through the unitaries. I pass through the bonds, and I do something like this, passing through the bonds. And if this were, say, my initial state lived here, this would be a valid way to end my cut. Okay, so it ends at the bottom, in this case, at the initial time of the quantum circuit, right? And the statement is that the number of bonds cut by gamma, it provides an upper bound on any Renyi entropy, or is related to an upper bound on any Renyi entropy. This is kind of intuitive. What you can imagine, I'll just say it in words. You can imagine that every such cut partitions the wave function into a product of two tensors, right? And those tensors are being contracted across the legs that cut through this curve gamma, right? Okay, so in the kind of MPS language, it's as if I have a wave function whose bond dimension across this cut is related to the number of curves cut by gamma, and therefore that's related to the entanglement. The number of such bonds is specifically related to the rank, an upper bound on the rank of the reduced density matrix on A, which we know provides a bound on all of the Renyi entropies, right? Okay, so okay, so I haven't told you what. So given this curve, then any Renyi entropy is upper bounded by log of Q. So Q is still the local Hilbert space dimension times the minimum of the following quantities. So this is the number of sites in A. So there's NA sites here, N A bar, qubits in A bar, and where N gamma is the number of bonds that this curve gamma intersects. Okay. Are there questions about the prescription? Yeah, that's right. So you're allowed to exit via the left and right boundaries also, although I don't have those in my setup right now. Yeah.
And the upper bound for rank or equal to?
No, it's an upper bound on the rank. It's generically it'll be saturated. But yeah.
So for qubits, does it set?
Sorry?
For qubits, does it saturate?
For Q?
Qubits.
Oh, for qubits. Well, it depends on the circuit, right? Like, you could imagine, a trivial example is the following. I start with states that are product state in the Pauli Z basis, and I apply gates that are diagonal in the Z basis. Of course, the entanglement isn't. Oh, for Haar. Oh, I see. Yeah, for Haar random circuits, I think it's pretty close to being saturated. The rank is pretty close to being saturated by the minimum cut. I think you can argue that typically it should be, but the rank, of course, is sort of a sick measure of entanglement. So we're just using it to bound quantities we are interested in. Yeah. Oh, so you mean what's on the board or why this is true? Oh, why this is true. So that's in the notes, but also I'll say that you can imagine that the wave function at time t now is obtained as a contraction of two tensors. those two tensors for the cut, so every cut gamma defines such a contraction, right? So here I have one such tensor that looks like this, right? So this everything that I've drawn in green is like one tensor, which I'll call T1, and then everything over here. Sorry, the tensor should be extending out to spatial infinity on the left, but I didn't draw it that way. So this is T2, right? And T1 and T2 have these external legs, which are the physical legs of the wave function, but they're also contracted across the curve gamma, right? So if you sort of, you can think of psi as some sort of MPS type state, some tensor network type state where the bond dimension across this cut is given by the number of bonds intersected by this curve. And you can convince yourself that that is an upper bound on the rank of the reduced density matrix if I were to do a partition there. Yeah. Maybe another way of saying that is that I think the reduced density matrix on A you can think of as like T1, T2 times T1, T2 quantity dagger. Or sorry, T2, T1 times T2, T1 dagger. That's more or less what the reduced density matrix is. And so the minimum bond dimension of T1 and T2, the minimum Hilbert space that you're summing over is what determines the rank of the density matrix, since you're multiplying a bunch of matrices that are not square. Right? So if that's confusing, I can definitely answer that question offline. I'm going through that quickly intentionally, so you're not meant to understand why that's true. Just in the interest, if you don't understand it already, in the interest of time. Okay, I know it's supposed to be pedagogical, but I promise you the notes will explain that if that isn't obvious. So this is my scheme for cooking up an upper bound on the entanglement in any quantum circuit, right? So this is true for any quantum circuit you give me. So now we can apply this. So actually this itself is sort of interesting. So let me just say as an exercise, this minimum cut looks kind of innocent, but it gives some interesting results. So for example, in the brickwork, in any sort of, take a brickwork circuit, well, really in a generic quantum circuit, in 1+1 dimensions, I can think of the following geometry. I can start with the product state and imagine that I want to, at time t, compute, as a function of time, I want to compute the evolving, say, mutual information between, so I have a subregion, which I'll call A, a subregion, which I'll call C, and then I'll define B is the complement of, actually, sorry, and B is the middle. Oh, sorry, no, B is the complement of A union C. So it's the rest of the system. And let's say A is some, has D qubits in it, and C has D qubits, and B has, say, L qubits in it. And let me assume that D is greater than L, and I start with the product state. So if I start with the product state, the quantum mutual information between A and C is going to be 0, right? But at very, very late times, in a sort of generic quantum circuit, you might imagine without conservation laws that the reduced density matrix on AC is very close to infinite temperature. The quantum mutual information should also be 0, right? Because you're in an infinite temperature state. But by the minimum cut, what you would find is that at intermediate times, it's non-zero. So you can look at the mutual information between A and C, and IAC is defined as, it's SA plus SC minus SAC. This is an upper bound on connected correlations within A and C, right? And it'll look something like this. So as a function of time, and you can figure out for yourself how big this window is and how large the mutual information is. It'll be, well, actually the maximum mutual information will be extensive. So, which is kind of funny. In a structuralist quantum circuit, you obtain at intermediate times between two regions that are sort of close together, really non-trivial correlations, right? Even though and for those of you who are familiar, with the mutual information in a thermal state is always going to satisfy, with a local Hamiltonian, will satisfy a kind of area law. That's always true. And here we're going to an infinite temperature state. So it's like the sort of sick limit of that area law where it's 0. Yes. Oh, yeah. I'm not lower bounding SAC. I'm just saying the minimal cut prescription, maybe should be more explicit. The minimum cut prescription, if it were saturated, would give you this, right? No, I'm saying SAC, which is equal to SB, is also just given by the minimum cut through the quantum circuit, right? I'm saying, so the mutual information is SA plus SC minus SAC. SAC is equal to SB in a pure state, right? As I've defined B. And I'm just saying if the minimum cut genuinely gives me the entanglement SA, SB, yeah, if it's saturated, then you would have this behavior. We'll see in just a moment that it actually is saturated when you take the large local Hilbert space dimension limit of this quantum circuit. So this behavior you would actually see. It's not some pathology of the minimum cut. Okay. Okay, so now we're kind of ready to actually say something about the von Neumann entropy in the original circuit that we wanted to study. Okay, so let me draw this brickwork circuit again. So I'm just drawing one time step of the brickwork circuit. This is the arrow of time up here, and it's say. Yeah, this is A bar, and then this is A. So you can convince yourself that if I were to bound the entanglement based on the minimum cut prescription in this brickwork circuit, then all the cuts are really degenerate with each other, all the cuts that you would draw. For example, here's one example of a cut gamma that I can draw. It'll look like this. So this is just after one time step. And then it will keep going through the quantum circuit. Another cut that I could draw would look, like this. Okay, and both of these cut 2 bonds, right? And they'll end eventually at this initial time of the circuit, right? So all that we can say, and it's very trivial, is that the minimum cut gives me a bound on the entanglement, which is basically that any entanglement entropy has to grow slower than, and this is one time step, right? So this is one time step. So per time step, any cut that I draw, which will be the minimum cut, will any directed cut at least, which will be the okay, maybe I'll come back here and just say something very quickly. So let's say A and A bar are infinite. The best upper bound I can get, obviously, is by minimizing the cost of the number of bonds that gamma actually runs through, right? So that's the reason it's called the minimum cut prescription. And here, any directed cut through the circuit is a minimum cut, right? So, and such a cut will incur a cost, will intersect 2 times T bonds, so 2 bonds per time step, right? So from that, what do we find? Well, okay, we know that we know this is true. Let me just state it again. This is less than or equal to the Haar average of S of rho A. Okay, and this is now less than or equal to 2T log Q. So this is coming from the minimum cut. And this comes from convexity plus other stuff which has to do with the Renyi entropies being non-increasing as you increase the Renyi index. Yeah. Yeah.
This is for your brickwork.
This is for, sorry, yes. So let me say that again. So for the brickwork circuit, this is, now we're thinking about this brickwork circuit. Right, in the brickwork geometry, that's true. In generic circuit, that's obviously not true. Yeah. There will still be a degeneracy, but generally. But okay, can everyone see this, or is everyone on the, okay. Oh yeah, and just in the Oh, just that in the brickwork, it's obvious that there are many cuts that I can draw that are all degenerate with each other in terms of the costs that they incur, which I called n of gamma, right? Any directed cut in time is going to intersect 2 bonds per unit time. Now, if the cut turns backwards, it intersects more curves, more bonds rather, and then it costs more, and I'm not interested in that, right? Because I just want the optimal upper bound. Okay, any other questions? Yeah, so this bound, this is the minimum cut bound, which tells me that for every realization of the Haar circuit, this is true. The von Neumann entropy in any realization is going to be upper bounded in its growth by 2t log q, right? And then it's also true in expectation. Yeah. What have I written on the blackboard? Oh, this is too small. Okay, let me write that again, sorry. This, okay, let me write it below. There are seats up here too, I guess that might help, but okay. So I was just saying that this, I'll say it in words, this bound comes from convexity of the log, and then this followed by, other bounds on the Renyi entropies being non-increasing as you increase the Renyi index, and then this bound comes from the minimum cut prescription, okay? Now you can see it, or, yeah, okay, great. Okay, so let me just write this out explicitly. That so this means that so we've kind of sandwiched the Haar averaged von Neumann entropy, which is what we want to calculate, between these two quantities, right? These two functions. Okay, so something that should be, I'm just substituting in what we know to be true from the purity calculation that we did, right? Yeah. No, oh, sorry. Yes, there should be a 2 here. That's, yeah. Sorry about that. That was just an algebra error. Yeah, I'm not dropping anything. Okay, so right, so it should be clear that this bound is saturated on the left and right hand sides in the limit that the Hilbert space dimension becomes infinite, right? So in the limit that the Hilbert space dimension becomes infinite, we know exactly how the von Neumann entropy behaves, which is kind of satisfying, right? Not only do we know exactly how it behaves, the upper bound is saturated, right? So we know that it's not just true for, on average, it's true for typical instances of the Haar circuit, because this is the maximum value that the von Neumann entropy can possibly attain, right? Okay. Another way of saying this, and a more generic way of writing this also is, well, the von Neumann entropy is bounded in its growth by some linear function of time on the left and right hand sides. So it's just natural to guess that the von Neumann entropy also grows linearly in time to leading order, and its entanglement growth rate, which is often called an entanglement velocity, is now bounded as a function of q, right? So that's another way of writing this. If we imagine that this is given, really is given by vt plus subleading in time corrections, where v is often called an entanglement velocity, which is maybe a little bit confusing because we haven't introduced any length scales yet. It's a growth rate for now. It's not really a velocity. Then what we've shown is that 2 log of q squared plus 1 over 2q is less than or equal to v less than or equal to 2. Actually, sorry. Let me write it this way. It's often written like this. There's an overall factor of log q that's pulled out, and so this is log base q, and then there's 2 over here. So this is just notational convenience that this is like the equilibrium entropy density per qubit, right? Which is normally pulled out in the expression for when discussing the entanglement velocity. Okay, are there questions about this? Yeah. So the leading term on the left-hand side is going to be log Q, right? Yeah, but I mean, that's just a, yeah, right. I mean, it's log Q minus log 2, right? So the strict Q going to infinity limit, it is saturated. Yeah. Okay. There are many other ways to argue that in the large Hilbert space limit that the entanglement grows maximally. One actually nice argument is kind of relating it to relating this to Frank's talk is you can, in 1D you can have an MPS and then apply a unitary to that MPS, and then you can ask, like, if I were to if I apply a unitary across a bond and then I rewrite the resulting state in terms of, also as an MPS, what is the, minimum extent to which the bond dimension has to grow? And you can come up with some typical argument that it has to grow typically by, the rank of the density matrix is going to grow maximally. So this is kind of relating to the Karsh's question. Okay. Yes.
Also mentioned something. So this bound is on the expectation of the entropy, but you also said something about it.
Typical. Oh, the comment was just that if, in the Q going to infinity limit, not only is this bound saturated, but the upper bound on how quickly, this is an absolute upper bound on how quickly the von Neumann entropy can grow. Like, it can't be any larger than that either. So there's going to be no fluctuations in the entropy at Q equals infinity. So not only is it true in expectation, it's true typically at Q equals infinity because it's a bounded random variable, right? Yeah. Okay. Okay, let me just recap here and then move on to some other things. So in the Haar averaged S rho A grows ballistically and at the maximum rate in the Q going to infinity limit, and this ballistic growth is so often holds even with conserved quantities. And these are conserved quantities that are going to be maybe have for which propagate more slowly. So conserved densities that might propagate diffusively. Although you can talk to maybe Frank about this, that there are situations where higher Renyi entropies can grow more slowly than the von Neumann entropy, or Renyi entropies with Renyi index less than 1 in the case where you have conserved quantities, because there are large eigenvalues of the reduced density matrix that the Renyi entropies for Renyi index larger than 1 are sensitive to, which in a system with conserved quantities doesn't necessarily have to be decreasing exponentially in time. It can decrease slower than exponentially in time, and that happens often or cannot happen in systems with conserved quantities. So one last thing I'll say here before moving on. We've just talked about the Haar average S of rho. Right. The reason this V is known as an entanglement velocity is because it also governs the saturation of the entanglement entropy. So the saturation of the entanglement entropy has, when we talk about the saturation, we need to introduce a length scale, which is now the size of the subsystem whose entanglement is saturating, right? And not only does V govern the entanglement growth rate, but the time at which saturation occurs, the saturation time, is going to be more or less equal to the number of qubits in A, let me call it NA over this V, okay? So this gives rise, I'll say this in words without writing an equation, but this gives rise to scaling forms for the saturation of the entanglement for a finite subsystem. And those scaling forms are very well, there's great agreement between those scaling functions. So that tells you that entanglement grows at this speed and it also saturates in such a way, in this way, at a time that scales like this. So V is really a velocity. And those scaling forms, there's great agreement between numerics and what you predict were you to think of V as an actual velocity. So this ballistic growth holding with conserved quantities, to my knowledge, I first learned about this in a paper by Kim and Hughes I'll just say it's PRL 2013. The notes have the exact reference. Okay, great. So, so now I want to move on and discuss just the typical behavior of the entanglement very briefly. Well, actually, let me stop here and give some kind of big picture of where we want to go with all of this, because my own perspective on random circuits, and also with which are unitary or not unitary or what have you, is that this entanglement domain wall structure, which we've studied to learn about the von Neumann entropy, is a kind of universal structure that we can see elsewhere when we think about other observables, with or without symmetry. And it's really by bootstrapping these, statistical mechanical ingredients that I think I've learned a lot about entanglement growth and entanglement dynamics and quantum information theoretic measures in quantum many-body systems. So as a recap, and just to give a maybe big picture, so the purity, right? So this is e to the minus s2 of a in the random circuit, was mapped in, when I do the Haar average, to this Ising magnet in an ordered phase, where the Ising symmetry came from this exchange symmetry of multiple copies of the system. And it's the free energy cost of an Ising domain wall, which was related to sort of the entanglement entropy of the subsystem. This is very heuristic, right? But that's essentially what we found, right? The line tension of the domain wall gives rise to ballistic growth of entanglement. Okay, and unitarity requires that the Ising model itself has some additional special structure. It's not just a generic Ising model. It has this directed structure. The infinite temperature density matrix is an exact fixed point of the dynamics. Those all need to be demanded. Okay, so we may be interested in a limit of various quantities, a replica limit in the calculation, certain observables, which we kind of avoided for our discussion here. If one were to try to tackle the calculation of the Haar average, say von Neumann or Renyi entropies head on, you would want to calculate the trace of rho a to raise to some power, right? Do the Haar average and then take the n going to 1 limit or whatever appropriate replica limit would give you the Haar average of the log. And I kind of want to gloss over that discussion for now. But we may be interested in a replica limit. And when we do the replica trick, we know that the Weingarten function has additional structure. It's the permutation degree of freedom that become relevant, not just some Ising degrees of freedom. So in general, you might say, well, there's some statistical mechanics of a magnet with permutation symmetry, right? And it's more complicated than just the symmetry here. It's actually Sn cross Sn symmetry, and then there's an additional Z2 symmetry. We might talk about that. But for qualitative purposes, the Ising picture is actually quite good. For qualitatively understanding some, and without getting the quantitative details at all right, it's good for understanding some of the regimes of quantum many-bodied evolution with unitary or non-unitary evolution. And that's at least my perspective. It's okay. This calculation is to me an easy way of developing intuition about entanglement without worrying about the replica trick. So we intuition from the sort of 2 replica, which is this Ising picture. And here I just want to give you some sense for what that for what that really is. What that intuition leads us to kind of conclude, and this will extend on into some of the lectures next week probably as well. And there are probably other people in the audience who've also worked in this area who you can talk to. So so let me call this gaining intuition from the Ising picture. Okay, so we've already talked about probes of the ordered phase of the Ising magnet. And in the quantum many-body setup, this, all sorts of, we know that we have this bulk ordered phase, and depending on the observable we talk about in the 2 replica picture, we just change boundary conditions. So we're just looking at different probes of the ordered phase when we have this bulk unitary evolution, and we want to compute, say, the purity, the out of time ordered correlator, squared expectation values of observables. Those all look like very different quantities, but in the statistical mechanical picture, they're all just a change of boundary conditions, right? So they're all probes of the ordered phase. So we can call is a probe of the ordered phase. We can even say the out of time ordered correlators, which are related to operator spreading in the brickwork circuit, which David talked about, and et cetera, measures of correlations are all related to the line tension of the entanglement domain wall. The second is, well, you can ask, is there a order disorder transition for this Ising magnet? Can we do something to force this an order disorder transition? You can't with unitarity, because there are these weights that vanish that basically force the Ising magnet to be very close to essentially at 0 temperature, right? So, so let me say, is there an order disorder transition? And this is all very qualitative. This is really related to the measurement induced driven entanglement transition. And that's kind of intuitive. For those of you who are familiar with the measurement-induced entanglement phase transition, the entanglement entropy of monitored pure state trajectories goes from volume law scaling to area law scaling, right? Which is kind of like saying that the entanglement domain wall loses its line tension as you grow across the phase transition, right? So that's like an order disorder transition for the Ising magnet. Now, the universality class of that transition is not Ising at all. In fact, we don't know what it is in the generic case. But qualitatively, you might say this transition is just based on the Ising picture and some additional ingredients that we have to include, namely measurements, right? Okay. Yeah. Sorry, can you speak up? Yeah, that's right. In the higher replica case, you're asking about that. Yes, it will be, but those spins are permutation degrees of freedom, and there's a much more complicated symmetry. It's hard to study those models. Not only is there a much more complicated symmetry, in many of those instances, we don't know, unless we go to some fine-tuned limit, how to write that as a classical statistical mechanics, so with positive weights. So that's a technical point, but it's very important, right? So this is just like how I would use the Ising picture to get intuition about what one would do in quantum circuits and how you would get different regimes of quantum many-body evolution. And that's just by thinking about the Ising magnet and thinking about symmetries, right? Okay, and there's actually a lot to be said, a lot more than you would think. So this is, I would, see Raman Basir's lectures next week, which are going to focus on the measurement-induced entanglement phase transition. The third is, well, what about an external magnetic field? Symmetry breaking field. And we've already discussed how this is like coupling to an external environment. So this is like decoherence or dissipation. So the full state of the system is no longer pure. And you can use this to gain some intuition about how the entanglement should behave. basically when I have coupling to an external environment at very long times, if the environment repeatedly interacts with the system in some generic way, you would think the system would actually very quickly go into kind of an infinite temperature state. The infinite temperature state in the language that we've been using is like the up state in the when we've written down the statistical mechanics of the Ising domain wall. So the coupling to an external environment is like a field that prefers polarization along that up direction. That's essentially what ends up happening. Okay. There are other very interesting phase transitions that I also want to discuss. So the Ising domain wall is a directed domain wall, right? So in the unitary circuit. So you can also think of the directed motion of the Ising domain wall as just the imaginary time evolution of some free particle, right? In a system, right? Because the evolution is directed. And you can ask, well, are there phase transitions that particle can have? It has diffusive behavior. It's a sort of free particle. Can I introduce a potential or use some of these ingredients to essentially localize that particle? And there's that localization transition that one can drive as well. So these are for the top, number 4 is going to be some miscellanea. But I think all of these, I would venture a guess, at least the papers that I'm on, the intuition for those results came from thinking about the Ising picture and then thinking about the higher replica problems. So okay, so I'll call this pinning of the Ising domain wall. So this is like a localization transition. And this is going to be well outside the scope of what I'm going to be able to cover, but this turns out to be related to a phase transition in quantum information recovery when coupled to an external environment. So I'll just say, let me say it in words. This is a phase transition in quantum information recovery when you have initially locally accessible quantum information. It's evolving in some way unitarily, but also there's coupling to an external environment. So the worry is that in purely unitary evolution, any information in the initial state, as we've already discussed, is always going to remain in the state at some time. It might be very hard to recover because of quantum chaos, but you could just invert the unitary dynamics and return to the initial state and have the same quantum information that you had. That's not true if you have explicit dissipation. And so there is an interesting question of if you have certain kinds of dissipation, does quantum information encoded in a many-body system leak to the environment or stay in the system? And that phase transition, which is not a phase transition. So here I'm not dealing with the sort of semantics. I mean, they're not semantics, they're important. Here I'm not dealing with the question of whether an observable is technically observable or not. I'm dealing with the more literal question of whether the information actually is in the system or is not. And I'm not at all dealing with how easy it is to recover if it remains within the system, right? Which is more related to the question of chaos and things like this that David was discussing. Yes. Yes. Yeah, that's right. Yeah. Oh, I have to couple to an external environment. I have to perturb the model to change the model, right? Yeah, I'm changing the brickwork circuit. I'm now listing off, so I would change the brickwork circuit so it's not purely unitary evolution on an initial state. It's also coupling to an external environment, and that's kind of what I'm saying. So I'm asking, maybe what I'm writing here is, what is the ingredient that I have to introduce in the brickwork circuit that corresponds to an external symmetry breaking field? And that ingredient turns out to be coupling to an external environment. So I have to change the brickwork circuit. It's not unitary anymore. It's an open system evolution. Right. Okay. Yes. Yeah. Actually, these two things are intimately related. I can. Where did I leave my iPad? There it is. Maybe I can discuss this a little bit more during the coffee break, but I can just say the following: that in this random circuit, we had this A subsystem and A bar, right? Okay, so there was an entanglement domain wall that was nucleated at the interface. And it turns out that so if I think of this as a subregion of a much larger quantum many-body system, then it's like I have dissipation at the boundaries, right? I have some bath, which is the rest of my system that's coupling to the system at the boundaries. And according to point 3, that should act like a symmetry breaking field when I think about the dynamics of this system. So there's of the open quantum dynamics of this subregion. So there's some symmetry breaking field that lives on the boundaries here. Okay. Right. And it turns out that this symmetry breaking field can act like a potential for this Ising domain wall that prefers that the domain wall gets pinned to it or is pushed away from it. So let me neglect this boundary for now, just for in the interest of time and simplicity. So I really have this problem of an Ising domain wall that can right. So let me say this very quickly and then move on. Actually, yeah, let me just leave it sort of schematically. So, and I can discuss this offline. So we have an Ising domain wall, and the Ising domain wall can either end at this interface or be pushed out at this interface. And the strength of the dissipation acts like the strength of the potential for the Ising domain wall. But since the domain wall is directed, you can think of this problem as the imaginary time evolution of a quantum particle in the presence of a potential, but on a sort of semi-infinite line, right? And there's a localization transition. So we're all familiar with like a particle on an infinite line with a delta function, potential, and there you always form a bound state. But if you have a semi-infinite line, there's actually a threshold above which you form a bound state. So this phase transition, you can think about what this means, and it turns out this is related to if I encode an order 1 amount of quantum information in this system, does it get lost to the environment or stay within the system? Yeah. Yeah, so let me see. I think the potential is actually repulsive, and I think the domain wall would prefer to just stick to the interface. Let me discuss that offline, just because I want to get to a few other things. And
the threshold, because now you need a first excited state of the of the full. You're putting a boundary condition, but that's like the symmetric wave function is not allowed.
Yeah, exactly. Yeah, that's one way to think about it. Yeah, right. Yes. Sure. Well, you're probably right. Let me just discuss a few other things, because I think the question that led to this discussion was already a bit of a sidetracking, but I would love to discuss this offline and coffee break and whatever. So this is yeah.
In none of these, the feature where there's a domain wall in the presence of quench disorder, but I recall there was a
yeah, that's the next thing I'm going to get to. So that's what the replica trick actually gives us, which is kind of important. Okay. So let me just say, so there are a bunch of references in the notes. So this work is work with Utkarsh Agarwal and Isabella Lovas, which came out a few months ago. There's other interesting work about phase transitions in quantum information recovery in the presence of dissipation, where the dissipation is different to this. There's a paper by Zach, I think Weinstein, and Ehud Altman, and other authors whose names I'm forgetting, which is when there's bulk dissipation. And there, you can also think of that phase transition in the Ising domain wall picture, I think, but still there's, in terms of out of time order correlators and things like this. So this is by no means exhaustive, and there's this work and other works that one should look at. There's also this pinning transition, there are other kinds of phase transitions that can happen. The notes discuss this. So we know that, I'll just say this in words since I'm kind of doing a survey. We know that a typical operator under unitary unstructured, minimal quantum circuit evolution will spread ballistically, and David discussed this in a random circuit. But you can ask, what are the operator histories? Because the operator spreads into a bunch of different kinds of operators, and I can think of each of the Pauli strings that an operator spreads into as like a different sort of wave function for that operator with a particular amplitude, right? And you can ask, which of those amplitudes contribute to correlation functions of real-time correlations in the random quantum circuit? And it turns out that in that setting, you can actually have phase transitions in what kinds of operator histories contribute to different kinds of real-time correlation functions. And that's also described by a different kind of pinning/localization transition now for multiple directed paths. And the statement is basically that, there's certain real-time correlation functions in the quantum circuit. So I'm thinking about a 2-point function of local operators separated in space-time, for which the dominant contribution to that correlation function will be operators spreading ballistically and then sort of refocusing back into a point. But depending on which correlation function you choose and how space-like these points are separated, you'll find that the dominant contribution actually comes from rare trajectories of the operator evolution. Not typical trajectories where it grows ballistically, but rare trajectories where the operator only grows to an order 1 size. And that's related also to a kind of pinning transition or localization transition for multiple directed paths. Okay. Anyway, I'm going through this a little bit quickly also because the references and maybe full sentences that discuss this are also included in the notes, but I want to encourage maybe discussion and questions. So, and sort of get through more things before I'm done. Okay, so let me finally discuss the sort of final topic that I'm going to discuss, unfortunately. So is really what happens to the von Neumann entropy in the circuit away from this Q going to infinity limit. And what I mean, what happens to it is there's a good reason to believe that the von Neumann entropy grows ballistically, but is that really the full story for how the von Neumann entropy actually grows in time away from the Q going to infinity limit? So in this limit, we know how it grows typically. We know it's just strict ballistic growth with some velocity that's saturated by that upper bound. But what happens to the von Neumann entropy away from Q equals infinity? And we can argue that in the brickwork Haar circuit, that the von Neumann entropy, well, I'm going to be formal and really quote this in terms of the second Renyi entropy, because this is, I think, where we have a really good argument for this, is given by so in the brickwork Haar circuit, we can argue that the second Renyi entropy grows ballistically in time, but it has a universal subleading correction. And it's normally written in this way. So the entanglement entropy is written here as a random variable, right? It's written as a random variable. Chi here is a random variable. Of order 1 size. It's a function of time, but it's some order 1 quantity. So the statement is that if I take the expectation value of the second Renyi entropy, what I'll find is ballistic growth plus a universal subleading power law correction to the entanglement that grows with a universal exponent, which is t to the 1/3. Okay. This t to the 1/3 also governs fluctuations of the entanglement. Fluctuations the mean also grow like t to the 1/3. And this basically establishes that the leading order ballistic growth of the entanglement is a feature that holds in every realization of the Haar circuit, right? The fluctuations are small. And I'll, in the remaining time, just present what the schematic argument is for this, right? This might also connect to some things that Raman will discuss next week. A similar structure actually emerges in the volume law phase of dynamics with a weak rate of measurements. Okay. Okay, so let's consider the replica trick for the second Renyi entropy. So for the second entropy, the replica trick is basically von Neumann entropy. I'll write it down trivially for the second Renyi entropy. It's given by 1 minus trace of rho A squared to the K divided by K, and the K going to 0 limit. This is something that you can check. So this will give me, right, this will give me minus log of trace rho A squared. Okay. So what we want to do now at least, is to figure out what the Haar average of this looks like, right? And if I calculate the Haar average of this quantity by the replica trick, I really need to calculate the Haar average of this guy over here, right? And when I do that, I'm going to obtain many more than the 4 unitaries we had before, right? So, so trace of rho A squared to the K involves sort of, if U of T is the quantum circuit, it involves U tensor U star, but this is tensor 2K times, right? So when K is equal to 1, this was the calculation we just did, right? Or, it's similar to the calculation that we just did. And when K is larger than 1, you get 2K copies of U times U star. So after Haar averaging, we get these permutation degrees of freedom, which I'll call sigma and tau, which live in the permutation group S2K, right? It's the permutation group on 2K elements, right? And K equals 1 again gives you the result that we were studying before. Okay, so it looks like this looks tough, right? And it looks kind of annoying. But one thing that we can do is to notice that, so we have shown the following, so that in the limit Q goes to infinity of the Haar average of S2, right, is exactly equal to the limit Q going to infinity of minus log the expectation value of the purity, right? Right, this is what we showed. And this is true of the strict Q going to infinity limit. Okay.
You have infinity coping.
Sorry? Yeah, but you can also measure this in units of log Q, right? So in that case, yeah, which is the natural way you would measure entanglement purity. So, right. Sorry, there was a question here. Okay. Yeah, so this is what we've shown. And actually, this means something really, really simple. So the Q going to infinity limit somehow is so simple that we can calculate things exactly, right? And the replica trick should really simplify, right? Or when we do the replica trick, things should really simplify. And you can convince yourself that if I denote Z sub K, if I define this to just be the Haar average of trace of rho A squared to the kth power, right? So again, K equals 1 would have been the Ising case that we studied. Okay. So then you can convince yourself that, this relation here, the fact that in the Q going to infinity limit, those two expressions agree, the log of the average of the log are identical, actually means when we think about the replica trick for the second Rényi entropy, that this quantity is actually exactly equal in the Q going to infinity limit to the Haar average of the purity raised to the kth power, right? So another way of saying this is, so in the limit Q goes to infinity of ZK is actually just equal to Z1 to the kth power. This is the statement, this is equivalent to this equation and using the replica trick. So this is, so in order to be consistent with that expression up at the top, this has to be true, okay? So what does that mean? What is this quantity here? These are just K non-interacting copies of this Ising problem that we studied, right? Just completely non-interacting copies. So Z1 to the K is just K non-interacting copies of the Ising problem we just studied. And somehow when you turn on 1 over Q, something goes, something's funny happens, right? Something interesting happens. And it turns out the most natural thing you might argue is that, okay, I have these K copies, and in each one of them, I have one of these Ising domain walls, right? Because we're calculating the purity. So I have K copies. In each one of them, I have this Ising domain wall. This is A bar, and it's doing its own thing in each of the copies, right? Etc. This is in the Q going to infinity limit. At leading order 1 over Q, you might suspect, well, maybe there's inter-replica interactions, right? There are interactions between the different replicas, and you can ask, well, can we figure out what those inter-replica interactions are? This is what we do. We hope for simplicity, and the answer is that indeed, yes, at leading order in 1 over Q, there are attractive inter-replica interactions between pairs of replicas. So this is just the sketch of the argument. And this calculation is actually quite complicated, but at leading order in 1 over Q, there are attractive inter-replica interactions. And in the notes, kind of go roughly over this calculation. It shows up at some very high order, 1 over Q to the 4th or something. But so as a result, so Z of K is really describing K directed paths. Well, actually, let me write the expectation value over the Haar measure of S2 of A is really describing K directed paths in with attractive interactions in the replica limit, right? That's what you would argue in the large Q limit of this problem. Okay. Well, this is like we did the replica trick, but you can also undo the replica trick. And it turns out this problem is very famous, the problem of K-directed paths with attractive interactions in the K going to 0 limit. This is the replicated description So let me write it this way. This is the replica trick, a different replica trick that you would do to calculate the quenched average free energy of a classical statistical mechanics problem. This is the replicated description of this problem known as the directed polymer in a random environment. And the directed polymer in a random environment has the following description. I'll finish. The thing is, the only organizer here, I have the benefit of chairing my own session, so I can end as late as I want to. Leo's frowning at me. Yeah. I'll just state one thing and then wrap up. I'll say it in words. The directed polymer in a random environment just describes a path in this two-dimensional potential landscape, a directed path. That potential landscape is random, but it's short-range correlated in space-time. So if one were to calculate the quenched average free energy of that problem, you would do the replica trick. You would obtain many copies of your system. Now there's no disorder, but you replace the disorder by attractive pairwise interactions between, or whatever kind of interaction between the paths, right? And then you would take exactly the same replica limit to get the free energy of that problem. So the conjecture is that, in the large Q limit, the free energy of the directed polymer in a random environment, really the free energy, has the same scaling as the second Renyi entropy. We believe it also holds for the von Neumann entropy, et cetera. But that gives rise to this T to the 1/3 correction and other very sort of interesting phenomena. So, okay, so unfortunately, I wasn't able to talk about structured circuits, and in the notes I talk about it a little bit, and I go through I think a kind of interesting calculation of the emergence of random matrix statistics in Floquet Haar random circuits. So there, the StatMech problem is dressed by all sorts of other structure because you have time translation symmetry in addition to just unitarity and locality. So it's not this Ising magnet anymore. It's some kind of Potts model that one has to study. But anyway, I'm happy to answer any other questions that you might have since I'm kind of over time. So thanks. Let me start from the left. Yeah.
Well, is it obvious that you can like commute limit and expectation value? It's not always true, right? So when is it true?
Yeah, you're saying like, is it obvious that when I take the expectation value, I can move it inside of the limit?
Yeah.
Uh,
I don't think it's treated like general.
right. I mean, this is a function that's bounded, right, in its value in each realization of the circuits. I think there'd be that much of a problem in doing this. Like trace Roy squared to the kth power is perfectly bounded for every realization. So yeah. Was there a question here or no?
So you mean by attractive, you mean like the domain was attractive?
Yeah, so if I were to write down a sort of path integral description of this system, yeah, there would be some attractive interaction in space-time. So when the domain walls are near us, the same space-time point, it costs less action. Yeah. Yeah. Well, I don't really know that I would call it a classical limit, but in what sense? Like you're saying, like in the large S expansion or something. Yeah. I actually don't think of these problems as being classical, like the, well, okay, you're asking if there's a classical problem that you can study in the limit of infinite Hilbert space. Maybe I'm confused by the question. I thought we just went over a description of this as a classical problem that, which holds, I guess, even away from infinite Q. Maybe I'm just being confused by what you're asking. Yeah. Yeah, Frank? That's also true. Yeah, that's something that, yeah, so that's also related to the directed polymer. So in the, we've basically determined the entanglement grows maximally in this Haar random circuit. Now, if I have geometrical randomness in the circuit, so it doesn't have a brickwork structure and the unitaries are applied randomly, then you can think of the entanglement across, a cut. So I have a semi-infinite system. I have a cut at a point X, and say everything to the left of it I call A. So, S of X will grow maximally when I apply a unitary across the cut in the limit of infinite Hilbert space dimension. But what does it mean to grow maximally? Well, it's a von Neumann entropy, so it still has to satisfy subadditivity, strong subadditivity, et cetera. So it'll grow maximally subject to those constraints. And when you write down that problem with randomly applied gates in space-time, so now there's spatiotemporal randomness, then you get this surface growth problem that Frank was talking about, where you can think of S of X as the height of an interface that's growing.
That's just why you got to work there.
Yes, so the directed polymer is and KPZ are kind of different descriptions, and there's a third description as well, which we haven't discussed, but shows up in some Clifford circuits. Yeah, K is the number of copies of this Ising domain wall problem. It's a formal limit, right? I'm formally taking that limit in calculating the second Renyi entropy. So what do you mean by what do you mean? Like, yeah, there are no paths, but that kind of thing happens in statistical mechanics a lot, right? Like people often say that Q going to one limit of a Q state Potts model is like describes percolation. But what does it mean to have one state on every site? Well, it's a formal statement. There's some version of the problem where you can treat K as as just a free parameter, and then you can take that limit formally. Yeah, right. Yeah. In the leading term, well, I mentioned very briefly that with conservation laws, you can get like with a U1 charge that's conserved in 1D, you can actually get for the higher Renyi entropies, root T growth instead of the leading behavior being ballistic in time. But the Renyi entropy will generically still grow, or sorry, the von Neumann entropy will generically still grow ballistically. So that might be an example. But in the absence of conservation laws, unless there's some very special structure to the circuit, I don't think that would be possible.
Another example is random.
Oh yeah, that's true. So we haven't talked about integrable systems. So in integrable dynamics, you can get that. Yeah. Sorry, can you speak up? It's hard to hear. Yeah. Yeah, so you can play, exactly. So you can play with these models and get, you can try to engineer that kind of potential if you want. I haven't thought about that too much, but yeah, like for instance, you could in the surface growth language, you could modify the randomness in the surface growth problem so that it's not just short range correlated in space time, it's correlated in some other way. Maybe that's related to what you're saying. So the disorder the directed polymer sees isn't just short range correlated. And that's in a different, I think if it's long range correlated in space time, there's a different universality class for that problem, if it's sufficiently long range correlated, but I'm not so familiar with that. Yeah, Ali.
Interesting, sounds like negativity at the end. Is it just like changing the boundary to something else?
Yeah, there's like a swap operator you have to apply at the boundary that does the partial transposition that you need for the negativity. The negativity is interesting because we know that, so here the sort of two replica case, which is the purity, is like the simplest quantity I can compute that's related to the entanglement. But for the negativity, simplest quantity that, trace rho partial transpose A squared behaves exactly the same as the purity, right? So if you were to calculate the negativity, you have to go to the three replica problem, and that's the first sort of non-trivial instance. Yeah.
Interesting thing other than
Yeah. So they're like I mentioned just verbally that there's like space-time correlations of local operators in these circuits, right? That you can think about. Now those will always decay exponentially, in time, but the rate at which they decay actually is sensitive to some of these phase transitions that I discussed. There's references in the notes. I didn't want to write them up on and the notes have not been uploaded. Yeah, Leo, should we break for, oh yeah, no.
So it's the property of the Weingart function that there's no domain law, the U at zero temperature, there's no domain law, the weight is one, that's some summation. I didn't.
Yeah, so that's forgetting the Weingarten function for a moment, that's a consequence of unitarity, right? Yeah. Yeah, so that's a consequence of unitarity because Yeah, so if I, I have this kind of problem that I was thinking about, U star, U and U star. The up state, right, is the state where I've contracted. So if I contract this against the up state, I've attached these two legs together and these two legs together, but that's just contracting, this is matrix multiplication of U and U dagger. So I just get here the identity, and then here I also get the identity, right? So in every realization of any quantum circuit, in any quantum circuit I choose, if I contract the sort of this replicated operator on what I'd called the up state, I always get the up state back, right? And you can kind of convince yourself that this downward facing triangle having weight 1 in the, once you do the Haar average, is just a consequence of this. Yeah, I mean, it's a consequence of that and the, yeah.
Both of those are one.
Both of those are eigenstates, right? Because they just involve contracting U and U star across the different copies.
So the triangles weight 1. There's
Independent of whether it's up or down, exactly. And it's easy to see why it's true for the up state, and then just by the symmetry, it has to be true for the down state also. Yeah, Karsh.
This T power 1 over C behavior, that's a big.
Yeah.
How universal is it true for chaotic Hamiltonian?
Yeah, so time dependent Hamiltonians, I guess I think in Brownian circuits, there's an argument as to why this should also hold. Yeah. But as far as the numerical status of seeing it, I'm actually not so familiar with that. It's been, yeah.
Is it true for Clifford?
Yeah, it's true for Clifford, but in Clifford, there's strong fluctuations between realizations of the Clifford circuit. So it's true if I take an ensemble of Clifford circuits, it's true. Yeah. Next order in 1 over Q. Well, I mean, it gets more complicated, but I think we kind of want to think about this from a sort of maybe in like an RG type standpoint, right? Like if you have these K paths that are completely non-interacting, that's one fixed point. And then you can ask, are attractive interactions a relevant direction or not? They are. So that's a relevant perturbation. And we know what that flows to. It flows to this directed polymer kind of fixed point. And then when you're sitting there, it's, unless you add in, something else like, you make the disorder long range correlated or something, that fixed point is pretty stable. So I don't think anything else will happen at higher order in 1 over Q. Now the entanglement velocity continues to be renormalized at higher and higher order in Q. So that happens. But those are details. But I think the T to the 1/3 behavior should still be there. So it's a conjecture that when you actually go to Q, finite Q, like Q equals 2, that we should also see this kind of behavior, and we do numerically. Okay, so as the chair of my session, maybe we can go to coffee. Oh yeah, right.